Oh, hi, Jessica. You're early? Hi, Juan. Zhonghuan, right? And you know what? This is December already. Time flies, right? So the first time you guys tuning for the lectures, it was September. And it's now already December. And you know what? This is the happiest season of all. The Christmas is coming. Yeah, I know it is a little bit strange, you know, living through Christmas in Taiwan. It just doesn't feel the same. I understand. Oh, hi, Liang Yu. Yan Yo. And Wei Yo. You know what? Yan Yo from Team 1 and Wei Yo from Team 4. You guys made an impression last week, right? Winning the first round, stage 1, and winning the round 2, stage 2. Good job. Yeah, Mao, you're, I think, Wei Yo's teammate. Yeah, good morning, Borji. Well, actually, good afternoon, Borji. Great, so good to see that Wei Yo, Qimao, you guys are working great together. I think Yan Yo and Yu Xiang are working great together. perfect time to get started. Oh yeah, good to see you guys here. Chien, Livia, Li Jun, Boris, hi, how are ya? Eximin? Yeah, I like your ID, Eximin. Liang Yu, it's pretty cold today. I understand, right? Then it's really nice to be able to attend virtually. So from within your room. Hi Shanting, hi Yanjun, good. And the bell rings. Let's go ahead and start. So to do for this week, we just have one quiz this weekend due. Okay, good for you. But not so good for you. For many of you guys, exam 2 is coming tomorrow. I understand as you guys have went through so many exams, I understand the adrenaline pumps up, but you also get this extra anxiety as well. That's what's making exams hard to cope with. I know it would take a while, maybe until 大四 or maybe later, that you can be a little bit easy with the exams. Okay. So tomorrow exams is coming up. Okay. And I have tried to ease the level of the exam a little bit given the outcome of the first exam. Okay. Because after all, the exams are not really to frustrate you, but to let you know how well you do. Okay, so if it's too challenging, then it sometimes kills the motivation. I know I had this, sweater. It's a sweater coat, a Japanese type of coat. Not quite the Western, the trench coat or major wool-based coat. So this is just the right level. So I hope that you guys all dress warm. Okay, Yunqi, yeah, Shanting, yeah. If you live nearby, I think with the rain and slight rain going on, it might get colder, even later into the afternoon. Okay, another professor said that the weather today is just like spring in Chicago. You know what? It is. It is. Also a little bit like Boston. Hi, Xian. Well, Xian FX is another misery attenders of the lectures. Hi, Justin. Yu Hao. I almost miss you guys. And Yan Jun. Every week this month. You have. Oh, sorry about that, Yunqi. Ouch. Okay. Oh. Hey, extra love for Yunqi, guys. Let's do this. Hard. Extra hard for Yunqi. Okay, let's show some support. All right. Okay, poor you. But lots of love from us. Okay. It is December now, Qinglao. And hi, team. Yeah, Yanjun, let's show a lot of love, okay? Yeah, because, hey, we cannot run away from exams. So what else can we do, right? Yeah, we just, keep loving. That should pull us off and through the semester. Great. Yeah. Yeah, so to be honest, Polly also had some trouble waking up in the morning today. Oh, of course, we're all here. Just think this way, hey, it's also hard for professors to give the exams. Okay, so professors are just as miserable as you guys. Okay, good. So now, let's kind of calm down a little bit and come back to the things that we're supposed to learn. Okay, the topics today. So what we'll be doing today is to transition from chapter 3 to chapter 4. And this is a big transition. We'll be leaving transport layer. Okay, until now, application layer, transport layer, everything we talk about is end to end. okay, from host to host. Okay, we set up connections, okay, from one process to another process. But later on today, you will see we'll be entering the network layer. Okay, that is a new world. Okay, we'll be setting up connections. Well, actually, not quite connections, but more like, connecting routers all the way, not just the end hosts. Okay, between a pair of end hosts, we have lots of these routers helping us passing on the packets all the way to the other end. Okay. Starting from chapter 4, we'll see what are the magics going on there, okay, making the routers work. But the first half is still, let's try to wrap up the remaining things we need to talk about in TCP's congestion control. Okay, first is about the, last week, if you recall, we have the sending window size. Okay, to address that the network is very dynamic. We could have high available bandwidth at some point, but the next moment, low available bandwidth because of lots of cross traffic coming in. Okay, so we adjust this sending window size dynamically according to the network condition, and we call that now formally the congestion window size. But you see also, the congestion window size is there to allow us to control the rate TCP sender is sending data out. Okay. There are some researchers around the world trying to analyze the sending rate so they can know better. For example, what is the average rate that TCP sender is sending traffic out? So, first topic here in terms of research in TCP. Modeling the sending rate of TCP.
Let's cover two more topics related to TCP, and these are about what the research community is doing trying to improve TCP for the future need. First is about how one improves TCP such that it can support long, fat pipe. Okay. What I meant by long pipe is a TCP connection that has long round trip time, and a fat pipe is that it has high throughput. Okay. And this is what we know. Okay. The sending rate or the throughput should equal the window size divided by round trip time. So this is 0.1 second. And the rate should be 10 gigabits per second. So you see, the congestion window is essentially the two terms multiply, and that is 1 gigabits and approximately 110 megabyte. So at the sender side, receiver side, 100 megabyte is required to buffer the packets that are in flight. And this is just to maintain one connection, right? If you have 10 connections, that's already 1 gigabyte of memory. If you have 100 connections, that's gonna probably take all your memory away. This is just one issue. Another issue is this. TCP is actually go back and like. What if you run into a packet loss that is triggered by having 3 duplicate adds? What we do there is we set the window size to half of the window size before the loss event is detected. And you know what? The window size, the number of packets there could be, can be as high as this, because if we divide this by 1500 byte, you get these many packets in flight. So in that case, we'll have to retransmit all the unacked packets, okay, and half of the window size here. Okay, so that's 41 and 666 something. Packets that we need to send. The bandwidth consumption there, right? The amount of bandwidth we might be wasting there is very significant. So TCP, the current design, isn't really ideal to support long fat pipes. And this is actually assuming that there's no packet loss at all, no bit error at all. What if we have error? One will have to derive the TCP throughput model considering loss before one can see how big a problem it is to try to support long fat pipes. So let's try to do some derivation here and see if we can come up with the average TCP throughput, okay, provided the window size, round trip time. The assumption is that let's ignore the slow start, okay? Consider just the congestion avoidance operation and assume that there's always data coming in. And the scenario is very simplistic, which is illustrated here. Over time, the changes of the window size is exactly from half of W increase all the way to W, and W is where the loss will always occur, and therefore we drop the window size back down to half W because this is in congestion avoidance. When there's a loss, drop to half W. When there's a loss at W, drop to half W. And so it's not hard for you to see what is the average window size? Yeah, the midpoint here, right? So 3/4 of W. And therefore the throughput is what? The average window size divided by the round trip time, which is this term here. Now, if we plug in, yeah, this is the goal throughput. And this is the round trip delay. Now, what is the window size now? Well, it will be this term multiplying each other and multiplying the reverse of 3/4. Therefore, it's 4/3 now. So this is actually even bigger than the CWND we're calculating there. So with loss, yeah, the amount of memory required to store data higher, the amount of unnecessary retransmission also higher. We can go on and on, right? Try to derive a more general model. So let me not go over the exact derivation, just tell you, if the loss probability is L, okay, one can actually come up with the TCP throughput being represented this way. Round trip time here, okay, square root of L here, and the maximum segment size here. Now, if take the same example here, take the same setting there. Packet size being 1500 bytes, round trip time being 100 milliseconds, and the goal throughput 10 gigabits per second. In order to achieve so, the loss rate needs to be as slow as this. 2 multiply 10 to the power of -10. Okay? Now this is a loss rate that's also impossible pretty much on the internet today. So definitely, we need new versions of TCP to support very high fat pipes going a long way.
All right. So that's just so that you see that trying to model TCP in a general way allow you to estimate how much buffer space you need at the sender, okay, or how big the window size needs to be, or how low the loss rate needs to be to achieve a certain performance goal. Next research issue is this, fairness.
Another major issue is this, fairness. Okay, let's talk about fairness at this level first, the TCP fairness. Okay, so what we're talking about here, the goal is to make sure that the K TCP sessions will share the same amount of bandwidth if it go across the same link of bandwidth R. So the eventual share of the sending rate or the throughput should be R divided by K. Okay, so in this scenario, what you're seeing is the router in the middle, the capacity is R, and we have 2 connections. So connection 1 here should have half of R, and connection 2 here should have the equal amount. So we have 2 competing TCP sessions, and they're competing for a link with capacity R. So what I'm showing here are the relationship of connection 1 and connection 2's throughput. So one extreme is connection 1 gets the whole R, while connection 2 gets nothing. And this is the other extreme. Connection 2 gets R, while connection 1 gets nothing. The fair point is right here in the middle. Okay, each of them gets half of R. So you see here, the dotted black line is to draw the equal bandwidth share, meaning if the bandwidth of connection 1 and 2 falls on this flat line, yeah, they'll be fair to each other. Now, the blue line here, okay, is actually illustrating, this is actually the boundary, the capacity of the link. Okay? If the sum of connection 1 and 2 throughput goes beyond the blue line, that means congestion is beginning to occur, packets will begin to drop. Now let's say we start from here. Connection 1 having this much throughput, while connection 2 have, very small throughput. As time goes by, okay, we're in congestion avoidance state, so we will continue to do additive increase. Therefore, connection 1's throughput will continue to increase, just like connection 2's throughput will continue to increase. And the characteristic, the value of connection 1 and 2's throughput will fall along this line here with the slope of 1. Now, as it goes beyond the blue line here, this is actually beyond the network capacity, we'll begin to see packet drop. And what we'll see next is what? The two of them reducing the throughput to half of the value here. Okay, so this is connection 2's. Connection 2's throughput drop to half of it. Okay, right down here. Connection 1's throughput drop to half of it, right down here. Okay. So having a loss, decrease the window size by a factor of 2. And that takes us from here down to here. So this is the current throughput of connection 1 and connection 2. Let's move on, right? It will continue to go additive increase as we are in the congestion avoidance state. Crossing the boundary of blue line, drop packet again, and decrease the window size again. Okay, again by factor of 2. So we go down here. So you see, additive increase, multiplicative decrease. Additive increase, you see, the throughput of connection 1 and 2 are actually what? Approaching the equal bandwidth share. TCP between the connections, the mechanism warrants that they will be fair to each other. So we see between TCP connections, they will be fair to each other. But what about TCP to UDP? Multimedia applications actually prefer not to use TCP because TCP has this window size mechanism when there's congestion drop it, right? So the rate sending rate is actually throttled by the congestion control mechanism. So some of the multimedia applications will prefer UDP, and they will send audio video data at high rate, constant rate without really, adapting to congestion. So would that be fair? Of course not. And not to mention this, what if you have applications who open up multiple parallel TCP connections? Okay, versus other applications who opens one TCP connection at a time to send data. Now consider this case. A link of rate R with 9 existing connections already, right? Then each have R over 9 share of the bandwidth. When there's a new app coming in asking for 1 TCP, that app then will share with 9 existing connections and each get 1/10 of the R. But if the new app comes in and then asks for 9 parallel TCP connections, so that would be what? R dividing by 9 plus 9. And each connection is this much because the new app gets 9 of these, so let's multiply this by 9. New app gets half of R. So a new app designing this way versus a new app designing this way, okay, competing with other existing connections, it's actually hard to make it fair. And you know what? Web browsers these days do this. Okay? They might start parallel connections to fetch one page. Previously, Internet Explorer were very aggressive. Okay, for example, starting 8 parallel connections, 4 parallel connections to try to fetch web objects in a page. But nowadays, the HTTP consortium actually regulates so that they do not overdo this.
All right, that takes us to the quiz of the week. Okay, so this is quiz 29. So we talked about within TCP, the connections will be fair to each other, okay, approaching this equal bandwidth share. Okay. And this somehow is because of the policy we use, right? AIMD, additive increase, multiplicative decrease. Okay. Let's see. With the two connections, okay, the same scenario we've checked in the video. With the two connections throughout, with the two connections throughput converge to equal bandwidth share, if the adaptation policy of the congestion window size is not quite AIMD, but Q1 asks whether we will get equal bandwidth share if we do AIAD, additive increase and additive decrease. Q2, what about multiplicative increase and multiplicative decrease? And last one, multiplicative increase and additive decrease. Okay, with these 3 other policies to adjust the window size, also take us to the equal bandwidth share. Okay, think about it, guys. So you might want to use the plot we have on the left here. Okay, and assume the starting point of connection 1 and connection 2's throughput the same as the example here. If it's additive increase and additive decrease, how would this red line here travel as time goes by? Okay. All right, so guys, think about it, and let me upload the PNG to the Slack channel. Oh wow, so you guys are really fast. Okay. I see, team 1 already say no, no, no. And team 4 also say no, no, no. Okay. So let's give the rest of the teams some time to think about it as well. Sorry, Ida. Well, let me roll back up so you can see the question. see Ida, your teammate is here to rescue you. Yeah, so Tim is here. All right. Everybody says no, no, no. Very good. You know what? Let's take a closer look, okay, into quiz 29. Oopsie. Yeah, so let's assume the same example, right? So we'll be starting from this point and then additive increase. So now let's consider the AIAD case. So this is additive increase, right? And now we hit the throughput limit, therefore capacity limit, therefore we'll be dropping. But this is what? AIAD, so we'll be also going down slowly like this, right? And we kind of just, stay on this slope equal 1 line here and going back and forth. So we know for AIAD, no, we don't come close to the equal bandwidth share. But what about MIMD? So multiplicative increase and multiplicative decrease. Then we will not be following this curve, right? Because this is additive increase. But connection 1 starts here and connection 2 starts here. If we double connection 1's throughput, so double, it should be about here, right? Connection 2 double about here. Okay, so if we do MI, then the throughput should increase like this. So the change of throughput for connection 1 and 2 should follow this straight line, right? But the slope is kind of lower than 1 and significantly lower than 1. It has something to do with the ratio of connection 1's throughput versus connection 2's throughput. So MI, MD, well, you know what? Come back down here. So MI, MD, MI, MD. We stay on this straight line here with the weird slope, lower than 1. Yeah, so we know, therefore, answer is also no. We are actually not closer to the equal bandwidth share. Now, last one, MIAD. So, well, MI we've tried, right? So it should come to some point over here, okay? As we exceed the capacity of the link, we need to begin dropping. But we drop in an additive way, which means we take the slope 1 down, right? And it's actually what? Driving us away from the equal bandwidth share. So this is even worse. It's a big no-no. All right, good. Oh, cool. Who did this? Great, you guys are doing great. Okay, look at this, guys. Let me see. Oh, extra point for team 5. Yeah, so team 5 actually shows exactly the scenario. Yeah, so in I think AIAD, we just stay on slope 1. For MIAD, the slope depends on the initial throughput, initial sending rate of connection 1 versus 2, right? And then the MIAD, we are actually walking away from the equal share. So you see also a little bit why AIMD is a great policy, isn't it? We make sure that all these TCP connections, no matter we are early starter or the late arrival, eventually, as we stay long enough, we will eventually share equal portion of the bandwidth. Okay, wonderful. So this is let's see. Oh wow. Okay, thunder. And what else I can give? Okay, a bow. How about that? Okay, a bow from Polly. All right. Great job. And with that, we conclude TCP. And we just do the last thing. Okay, there's actually a mode, a particular version in TCP's congestion control called ECN. And this is much earlier when some engineers were thinking about maybe we can come up with a network assisted approach solution. Okay, so let's hear out. The video is short, about 4 minutes.
That was TCP, taking the end-to-end approach. Let me introduce another mechanism that's called the ECN. It's also defined for TCP/IP for the internet, but it's not really implemented or activated. And it's taking the opposite approach, the network-assisted approach. The ECN mechanism works this way. First of all, in the IP packet header, okay, or network layer header, there's this special field called TOS that stands for type of service. So in that field, 2 of the bits are assigned for the purpose. They are also called the ECN bits. Okay, so I'm using a green packet here to indicate that that packet header, especially the network layer header, is carrying the ECN bits. They were initialized to 0, that means no congestion. But as the packet travels through the network, running into a busy router like this, the bits will be turned on. And the packet will eventually come, okay, and arrive at the receiver of the data. And the network layer here at the receiver is going to see, oh, these 2 bits are turned on, therefore notifying the transport layer. And at that point, the transport layer of the receiver is going to do this. Receiver is going to set the ECE bit on the packet going back to the data source, like this. Okay, so it's going to be in the ACK packet and the ECE bit being turned on. So this is also called the E flag, okay, in the TCP packet field. Sender there, upon receiving this ECE bit packet, will then send a packet that is then the data packet going back to the receiver. And that packet is a little bit special because there's also a special bit being turned on, the CWR bit. So this is congestion window reduced bit. This is so that the destination here, the receiver of the data here, knows that, okay, so my notification here, you indeed received it and reduced the sending rate. Okay, so therefore the receiver of the data does not need to send ECE bit again. Okay, otherwise, the source is going to reduce sending rate again and again. Right? And the E bit and the C bit, the E flag and the C flag are in fact again in the TCP packet header. Okay, so along with all these other flags for TCP. And that finally takes us to the summary of the chapter 3. We went through the basic functionalities of transport layer protocols: multiplexing, demultiplexing, reliable data transfer, flow control, and just now, congestion control. And we talk about how UDP and TCP implement these services. Particularly, we spend quite a lot of time here, as well as here. We are now finally ready to leave the network edge. So departing from the transport layer and down to the network layer and into the network core. But the network layer is going to be split into 2 chapters. Chapter 4 is going to be about the data plane, how we forward packets real fast. And chapter 5 is going to be the data plane. So how do we control these paths we select such that the packet will travel and eventually reaching the destination, reaching the receiver.
All right, so chapter 4, and let's start with the overview.
Welcome to chapter 4, the network layer, and particularly the data plane. So in this chapter, the goals are understanding the principles behind these network layer protocols. And we'll focus on data plane and talk about the other one, the control plane, in chapter 5. So in the overview section, we're going to talk about the service models possible for these network layer services. And we'll talk about the main functionalities that people implement in the network layer. Forwarding and routing. We'll talk more about these. And we'll be spending some time here talking about the architecture of a router and how packets travel through a router. And the rest of the chapter will be spending a lot more time here talking about forwarding of packets generally, as well as how it's implemented, how it's working on the internet. 4.1, the overview of network layer. Well, what the network layer is doing is simply this: transport segments from the sending host to the receiving host. So let's use the micro internet here as an example. And let's assume this guy here is the sending host, and this guy here is the receiving host. So the goal of the network layer service is so that we could send segments or packets through the internet to the receiving host. Now, what's a bit special though, in the network layer? It's not only the two end hosts have the network layer protocol implemented and operating on the machine. Each and every router inside the network here would also have the network layer protocols running. Now, to be exact, on the sending side, on the sending host here, the transport layer segments is going to be encapsulated into the datagrams. So a packet at the transport layer is called the segment. But when a packet now goes into the network layer, it's called a datagram. And sometimes also called the IP datagram. So transport layer, TCP layer. Network layer, IP layer. Transport layer, we have the TCP segments. Network layer, we have the IP datagrams. So at the sending side, we encapsulate these transport layer segments into the IP datagrams. Now these grams, datagrams, will go on to the network and travel from router to router. And each of the router will examine something special, in the packet header, in the IP datagram header, and decide where to pass it further on. So that magic we'll talk about more in the sections to come. Finally, when the packet arrives at the receiving side, so this is the receiving host, the network layer is going to look at the datagram, remove the packet header, and pass the segment up to the transport layer. So that is the lifetime of a packet traveling the network through the network layer. So in NMA, so a packet coming from above, pending the header, so packet gets a bit bigger, and you see routers busy forwarding the packet and eventually reaching the receiving host. And at the network layer header or the IP datagram header removed and the segment restored and pushed up to the higher layer. Alright, so that is the general picture of what the network layer protocol is doing. Now, the network layer protocol is doing two major functionalities. As you observed earlier, forwarding. The routers are all busy moving packets around from one router to another router. Hopefully it gets to the next router that is appropriate, so we don't take too much time to pass the packets until it reaches the receiving host. The other is this. This is also the magic that I was talking about. So this is the computation, the intelligence in the network layer that determines a route between a pair of sending host and the receiving host. Or a lot of times we just call them the source and the destinations. So to determine an end-to-end path to travel over the internet from the source to the destination. And that intelligence is also called the routing algorithms. An analogy is this. Let's assume the class is taking a trip to Canteen. I know the weather is getting warm. It would be really nice if we're in Canteen. Well, the thing you need to do first is this. routing, you pre-compute or you Google, okay, and come up with a plan, okay, for the day of travel. Whether we take a bus to the Taipei station or we take a metro to the Taipei station. And from the Taipei station, do we take the high-speed rail? And from the high-speed rail station at Kaohsiung, do we take another bus, or do we all rent a car or rent a number of these bikes so that we ride along all the way to Kenting? Okay, so the computation process, the intelligence that we need to do ahead of the travel is called the routing. Now, on the day of travel, we'll bring this Google map printout saying, hey, you start from home, you walk to a particular station, and you hop on a particular metro line. And once you get to the Taipei station, you just hop onto, high-speed rail number 112. And then after arriving at Kaohsiung, you go to a particular bus stop, and then you hop on the next vehicle taking you to Kenting. So that is this forwarding. Okay, so at every interchange point, you look up a piece of paper and find out what is the next step to do. So this way, it ensures that the forwarding part, the traveling part is going to be fast and smooth. So the separation or the differentiation between the routing function and the forwarding function.
All right. So I hope you get the idea. Forwarding, routing, different. Now let's take a closer look in the internet how these data and control. Forwarding is data plane. Routing is control plane. How these two functions are separated and running on different planes.
And that should make it a bit clear for you to see the separation between data plane and the control plane. So by data plane, we actually meant to talk about the forwarding function. Okay. And the control plane, on the other hand, is the routing function, the part that is trying to identify a path between the source and the destination. Now let's talk a bit more about the data plane. Okay, so what's being done there is very local. Each router is determining for each incoming datagram who should be the next router to forward it further. Okay. And that is the forwarding function. So it's illustrated here. For a datagram coming in, this router here is looking up a table and find out, oh, this should be the outgoing port, and therefore reaching the next router. Now, the control plane, on the other hand, is the part implementing the routing functionality, okay, implementing the intelligence. It is to determine, okay, how would the packets be able to travel end to end from the source to the destination. So these routing algorithms will be implemented in the control plane. Now there are two different approaches implementing the control plane. One is the traditional approach. The other is called the Sdn approach. Okay? The traditional one is the distributed approach. And the modern one, the Sdn one, is actually more centralized. Okay? To your surprise, isn't it? Okay, we are actually moving from distributed solution to centralized solution. Now in the traditional one, each router will be implementing the routing algorithm, and the routers will also exchange information among themselves. As a result, and collaboratively, they calculate an end-to-end path. Now, in this centralized approach, in the Sdn, we actually ask a couple very powerful machines, okay, a couple very powerful Sdn servers that are actually sitting far away, okay, from the routers to do the computation. And then after the computation is done, they're gonna install the routes back into the routers. Okay. So the tables are actually computed on the routers locally, okay, in the traditional way. But more recently, the modern way is to have some powerful machines computing all the routes and then install them back to the local routers. And local routers no longer do the complex route computation. So let's talk a bit more about the data plane. So this is the forwarding part. So this is the part implementing the per router action. Okay? And it's very simple, very fast. Okay? All that is done is the packet coming in. The router look at the specific packet header field and match to an entry in the forwarding table. Okay, so this is called the fast output interface lookup. Okay, once we get a match, we get also the outgoing interface. Okay, let me illustrate. So these are the routers. Okay, and inside the router, okay, you see this is the entire operating system stack. Okay, there's this thing called the forwarding table, and each router will have one of these. Okay, when there's a packet coming in like this, it's going to look into a packet header field, okay, and matching the pattern here to the entries in the table. Now, we see that this guy is the matching entry. Therefore, immediately we see the packet should go out on interface 2. Okay, so output interface 2. So this is the direction to forward the packet further, and therefore next is going to arrive here in this router. So this is exactly the detailed step of packet forwarding in the data plane. And the control plane is here, okay, higher up in the operating system stack. To be more exact, okay, and let's talk about the traditional approach first, where the computation is distributed. Okay, so the routing algorithm is going to be running on each of these routers, okay, and up here. Routing algorithm here, 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 and here. Okay. So each and every router, okay, is going to have the routing algorithms running, and they're going to interact with each other. So there are these exchanges of messages, okay, between these routing algorithms distributed on the routers. Okay. And this is the control plane. Okay. As a result of the computation and exchange, okay, they find out what should be the forwarding table, okay, for different incoming packet, for different packets going to different destinations, and install the local forwarding table into the data plane. So this is the separation of the control and the data plane. Now, in the modern days, we take the centralized approach, the Sdn approach. Now, it looks a little bit different, the separation of the data and control plane. So routers protocol stack, okay, stop right here, because the computation is all where? Up here. Okay, a couple machines, powerful machines, okay, doing the computation. But it cannot be computing without information provided by the routers here. So these routers, okay, will have a tiny little process running here. They're called the control agent. The control agent here is gonna provide input to the remote controller. This is the big process implementing the routing algorithm. So after collecting information about, hey, who they are and the connectivity of these routers to other neighboring routers, now this controller here can then do the powerful computation. Once the result is obtained, okay, those tables are communicated back, sent back to the control agent, and therefore installed into the data plane of the routers.
All right, so that was the overview of Chapter 4. It was very interesting, in fact. Chapter 4 and 5 are actually Polly's favorite chapters, okay? But we won't have time today to go on for more, so we'll just stop here. In case you guys have any questions, feel free to just type them up, either on YouTube chat or on Slack. Now, before you go, one of the students asked about the account you guys need to log in for the exams, right? For the exams, each of you will be using your own account, not the team account. Okay, so currently that individual account is not quite yet open for SSH access. Right after the lecture today, 10 minutes later, Polly will open it up so you guys can try logging back on and see if there are any issues. A little bit of advice is also that, hey, maybe you can try to upload some sample codes, okay, for problems in the exams that might ask you to do coding. Okay, good. So that's all. Type up your questions here, there, and let me resume the music, and I'll see you tomorrow. Okay. So tuning early so that would allow Polly to do the ID check a little bit earlier. So maybe we'll be able to finish the exam also a little bit earlier. Okay, and of course, I don't know who Dark Hood is, but lots of love. Okay, so exams are just a way to verify whether you are picking the technical stuff up. It's not really to frustrate you, but you see that I would not be a good teacher if I do not challenge you guys enough. So there'll be some tougher problems, but there'll be also some more fundamental problems. Okay. Okay, bye, guys. Bye. Oh, hi, Jessica.
Hi, Professor.
Hi.
So I have a quick question about the network-assisted congestion control. May I ask it here?
Yeah, sure.
So I went through the past papers, and I noted from the 2020 finals, problem number 8, that the congestion window size is adjusted based on the free buffer space and the queue size. And I was wondering how that happened.
I see. So you can probably imagine doing a calculation, right? First, measure in the router amount of packets arriving and how fast the buffer is filled up. And given the remaining amount of buffer, you can probably project what is the sending rate that this router can accommodate. So in a way that short answer is by looking at how much space is remaining in the queue and how fast the queue is filling up in the history. But longer answer is that, well, it requires some design as well.
Oh, so I assume there's a bit more than just turning on the ECN flag?
Yeah, it's not just that. So it's
I see.
ECN flag as well as a suggested window size.
Oh.
But I think one can actually think this way, right? By checking how fast the buffer is being filled up the last round trip time. Okay, so round trip time typically, if it's within US, no more than 100 milliseconds, but nowadays probably 50 milliseconds is typical. Okay, or within city, 20 milliseconds typical. So you could see how fast the buffer is filled up the last 20 milliseconds or last 50 milliseconds and see how much is remaining. And then you suggest the same amount of buffer space the last 20 milliseconds is occupying and send it back to the, I think send it with the ECN bit. After receiver gets it, receiver sends the notification to the sender. Sender take a look at that and set the congestion window size accordingly.
Oh.
And sender, of course, you see already in the video that sender also need to confirm. Yeah, I got it. I've already adjusted the sending rate. Otherwise, receiver might not know and then send another notification. And then the sender might slowing the sending rate down too much. So ECN, but what you can see also here is it's not exactly easy to find the right suggestion for the sending window size. Because there's also some delay to the receiver, some delay from the receiver back to the sender.
Oh, okay, I see. Thank you for the explanation.
Okay, I hope it's a little bit more clear.
It is.
But I think there's another RFC for the ECN type style TCP, but that is very old. I don't think that people are developing that version of TCP any further. So there's nothing more I can say in the lecture.
Oh, okay.
Okay, good. All right. Thank you for calling in.
Thank you for having me. Have a nice day.
You too. Bye.
Bye.
Oh, there you are. Hi, Eximent.
Hello, Polly.
Hi, Shengwei.
Hello. When I was, reviewing for exam 2, I have a problem.
Sure.
It's about fast recovery in TCP.
I see.
So once we receive 3 duplicate sequence, we will enter fast recovery state.
Right.
And so we have to resend the oldest ONAG sequence.
Yeah. Yes, we do that as well. Mm-hmm.
But isn't the timeout estimated for 1 RTT only? So we have to wait another resend and the egg to come back. But
Okay. Maybe we can take this a little bit slower. Mm-hmm. Okay, let me stop the music here. So you were asking in fast recovery. So first is that we see 3 duplicate eggs, right?
Yes.
And then we enter the fast recovery state. And as soon as we enter the recovery state, then we retransmit, right, from the oldest sequence number, essentially the same base.
Yes.
And this is likely the packet that is missing or delayed.
Yes.
Okay, and the question was we need to wait until another round trip time, right?
Yes, a new egg to come back.
Right. So in the meantime, what do we do? Or until then, what do? We will be still in the fast recovery state. Mm-hmm. And because of the change in window size, we can probably send the same base and maybe a few more. Okay. But then you see that in the fast recovery state, we kind of need to, it needs to be triggered by events. There are 3 kinds of events, I think, in the fast recovery state. One is receiving another duplicate egg. The other is receiving a new egg. And the last one is, of course, timeout.
Yes.
But you see that timeout is always longer than 1 round trip delay.
Oh, so once we enter fast recovery state, we will restart the timeout. Restart the timer.
Yeah, because we send again from the same base.
Okay.
That means the timer is restarted.
Okay.
Yeah. Because there's so in TCP, the full TCP, we do have 2 ways, 2 places. There are 3 places actually we start or restart timers, right? One is when we send the same base the first time. And then there are 2 other cases we restart timer. One is timeout, right? We resend the whole flight and then restart timer. And the last one is when we receive duplicate eggs, okay? Or, for the same base, the last one is duplicate egg. Let me think. You know what? In full... Okay, I see your question. Because in the finite state machine we did not include the fast recovery state. That's why things get confusing for you guys. Okay, this is a very good question. Thank you, Sungwei. I think maybe not maybe this is not gonna be fast enough for exam 2. But yes, yeah, so there's another place that we start the timer, but that is when we receive a ACK that we can move the send base. But that will be a timer for another send base, not quite for the old send base. With fast recovery, yeah, as we retransmit after getting the 3 duplicate ACKs, we restart the timer. Yes.
Okay. That answered my question. Thanks.
You're welcome.
Goodbye, Polly.
Okay, bye. Bye. Okay, so let me end the streams right here.